how to add and how to subtract. Okay, right? So next topic, subtopic, operations with complex numbers. Operations with complex numbers. Operations with complex numbers. Before this, something that came to my mind when we were doing the exercise, can I quickly just talk about something? Okay, I think this is something nice to think about. Now, when you have your complex plane like that, versus when you had the real number line in the beginning, right? You only had the real number line. Let me draw the real number line here. So this is when you only had the real number line, and now we have the whole plane. When you had the real number line, like if you think of, take any number, like say, let's take 2 right here, the number 2. The size of 2 is 2. And there was only one other number that had the same size. On the real number line, when we only had the real number line, there were only 2 numbers that had the same size. Whatever the size it is, there are always 2 numbers that have the same size. What other number has the size 2? If I take 2 as an example, the size of 2 is 2. The size of 2 is 2. There is one more number who has a size 2. What's that number? On the real line. -2. Very good, Nathani. Right over here. Had the same size 2. The size of -2 was also 2. So on the real number line, there were only 2 numbers that have the same size. Is that clear what I'm saying here? There are always 2 numbers that have the same size, only 2 numbers. Can you find it? Okay, Tarindu, we know you are Tarindu. Tarindu. Did we claim that you are Oshadi? Okay, anyway. Can you find another number on the real number line who has the size 2 other than 2 and -2? No. Okay. Now come to the complex plane. Here's your number 2 right here, who has a size of 2, and here's your number -2. Who also has a size of 2. Okay, Tarindu, now pay attention. Okay, so the number 2 has a size of 2. Here's your 0, size 2, and -2 has size 2. Can someone show me? Obviously, now there are more numbers who has the same size of 2, a size of 2, who is 2 units long, who has a magnitude of 2. Can someone annotate on the screen or tell me one more number that has the size 2? If I draw the number as a position vector, it will be more clear. So there's one. We only had those 2 when we were on the number line. Okay, Hatri says 2i. So the number right here, which is 2i, also has the same size 2i. I'm sorry, also has the same size 2. Ayyo, it's annoying. It's the same 2 units away from the 0. Can someone tell me another one? Are there any more? Now, these things are not like explicitly talked about in the syllabus, but these are fascinating. I just want to show you that. See, I'm starting to say is minus 2i. Very good. Yeah, the one right down here. Ayyo. Right here, minus 2i. Okay. Same size. It's 2 units away from the origin. Is that all? So now we have 4. We were on the real line. We had only 2 numbers that would have the same size. Now we have 4.
Miss, can we take root 2? Root 2 plus root 2i.
Root 2 plus?
Root 2i.
Yeah. So how does that work? So, I mean, I don't want you to come up. This is very good, Tarindu. You actually, Tarindu is saying root 2 plus root 2i. Find the magnitude of this. It would be 2. Is it 2? Oh. Yeah, it is 2.
Yeah, it's 2.
Right? I mean, what I want to, you don't need to tell me the number in a plus bi form, but look at this diagram. Shall I show you some more numbers who has the same magnitude? The one over here, the one over here, the one over here, over here, the one over here, the one. Do you see that there is a hole? Any number, oops. Any number on this circle, any number on this circle, there is a whole circle. I mean, any point, this one, this one, this one, this one, how many are there? How many numbers are there who has a size of 2? Hello? Anybody there?
Infinite.
Infinitely many.
Infinitely many numbers are there. You give me a size, whatever the size. How many numbers are there who has a size of 10? All the numbers on a circle with a radius 10, all those numbers have a size of 10 because all those points are 10 away from the origin. Okay, so Tarindu actually gave me like the actual number somewhere on this circumference. Isn't that like? That's just think about it. Okay. Right. Okay. I'm sorry that I took you out of the topic, but it's fascinating, isn't it? So size of 5. That's another circle with a size of 5. If this is 5 and that is minus 5, this is 5i and this is minus 5i. And all these numbers on this have a size of 5. Right? Okay. I don't know. I don't know whether you whether that was clear to you. Anyway, so let's look at how to do operations with complex numbers. It's very easy. We'll quickly do this. Because now what is a complex number? Anything in the form a plus bi. Any number we should be able to write any number in the form a plus bi. And how do you add numbers? Addition. We'll quickly do this. For addition, how do you do addition? This is very meaningful, makes sense. If you have like 2 plus 3i, that's one number, and you want to add to this 5 minus I, another complex number, it makes sense to say, okay, add the real parts together, add the imaginary parts together. They are the like parts. That should be the way we add complex numbers. No big deal. I mean, it's kind of obvious. It's we could have figured it out ourselves. Okay. So when you add complex numbers, it's just like an algebraic addition of like terms, real to real, imaginary to imaginary, just like we add vectors, I components to I components, j's to j's, case to case. You just add corresponding components. So that's how you do it. Add real parts together. Write with me. And add imaginary parts together. And you would get the answer, answer complex number. The answer must also be a complex number. So let's like just write an example. See, I want to add these two numbers. I will write on top the two numbers that I'm taking. My Z1 is 3 plus 2i. And my Z2 is 5 minus I. And I'm adding these two. I'll always take these two as the example when I add, subtract, multiply, and divide. It's easy. So if I want to add them, what's the answer? I simply, can I, wait, oops, I will forget what I wrote there actually. Let me do that now. What I'm doing here is, I'm doing Z1 plus Z2, that is 3 plus 2i plus 5 minus I, and that is just 3 and 5, 8 plus I. Okay? No big deal, right? I mean, that's how you would add it. It's very clear. Subtraction. Must be the same. You must be subtracting the real parts, subtracting the imaginary parts. Okay? Subtract. Because they are the like, Why does that happen? I don't know. Subtract real parts. Subtract imaginary parts. Example. If you want to do Z1 minus Z2, that would be 3 plus 2i minus 5 minus I. Just do the algebra. Let me remove like the brackets because I have, so minus 5 plus I equals to minus 2 plus 3i, correct? Addition and subtraction of complex numbers is quite obvious. I mean, how the way you have to do it is quite obvious. You work with the like parts. You simplify the like parts, like terms. It's like terms. Clear so far? Shall we go to multiplication? Yes, okay. Multiplication, I'll just try to write here itself. Multiplication, oops. if I had to multiply Z1 times Z2, again, I can think of it as algebraic, like usual multiplication. So expanding two brackets, removing two brackets, that's what you do. Okay. So you multiply like algebraically. That means, example, if you want to do Z1 times Z2, that would mean 3 plus 2i times 5 minus I, and you would just remove the brackets and multiply as if you were doing an algebraic removal of brackets, right? Like if you want to like actually this times this times that, this times this, and this times that, like that. Okay, the 4-step removal of a bracket. But remember, when you do I times I, what is I squared equal? You can simplify it. So let me actually like, yes, no, I times I squared is -1. Yeah. So what I get here is 15 minus 3i plus 10i minus 2i squared. Now, when I simplify this, remember I squared is, let me write that in red in brackets. I squared is -1. Remember that, you have to use it here now. So this is 15 I is minus 3i plus 10i is plus 7i. And this becomes plus 2. So this is actually 17 plus 7i. Is that clear? So that I squared, you have to simplify by taking it as -1, because we know that I squared is -1. So notice that you have to finally get a number in the form a plus bi. Your answer has to be in that form, the format a plus bi, because what you're getting is is also a complex number. Okay. Last operation, division. I will have to go to a new page. And I want you to think about, now just write division and don't write this. If you want to do Z1 over Z2, or you can write it like that, or you can write it like this, doesn't matter how you write it, they both mean the same thing. This would mean I want to do 3, what were the numbers? 3 plus 2i, 3 plus 2i divided by 5 minus I, 5 minus I. How do I do that? How do you do that? Finally, you have to get as the answer of this, or if I write it in this way, right? That. Now that is a little hard to think. How do I do that? So we use a technique here. And again, whoever who like realized, oh, we can do this little trick and somehow manipulate this division to obtain an answer. Hatvi says divide like polynomials. That's a very good suggestion. Like you mean like long division, a plus 2i. But the thing is this. Yeah, I mean, if you have to do like, what would it, just try to, but I like you that this came to your mind, polynomial division, but you try it and see whether that works. It doesn't work. you have to give the answer in a plus bi form finally. You know what we do? See how genius this is, okay? Now we can't multiply. It's like we do the same thing. Actually, this is not new. We do this in decimal division. Do you remember how we divide? When you have to divide by a decimal number, like say you want to divide 23 by 0.2. If you have to divide by a decimal number, now the top number can be anything. The problem is not in that. Now even in division of complex numbers, if I had to divide 5 plus 3i by 2 by a real number, fine, I can do that. This is equal to just 5 over 2 plus 3 over 2i. I have the a plus bi form. Right? I can divide a complex number by a pure real number, no problem. The problem comes up when I'm dividing, when this is a complex number. Then that also takes the form like 2 minus I, something like that. Go back to decimal division, division by a decimal number. Go back to division by a decimal number. Who remembers how did we do this? We can't do this. But so what we do is we work our way through it in a different manner. Instead of dividing 23 by 0.2, we change this into what? Because we don't know how to divide by a decimal number. How do we do this? Hello? How do we do this division? How do you divide 23 by 0.2?
Multiply denominator and numerator by 10.
Right.
First.
Yeah, see, right? We just change the form of the question by multiplying both the numerator and the denominator by 10. We make sure that we are dividing by a whole number. Then this becomes 230 and this becomes 2. And now we know how to do the division. So the trick here is this decimal number we change into a whole number. This is a whole number now. Division by a whole number we can manage. Division by a decimal we can't. So when you have to divide by a decimal number, you turn the decimal number into a whole number by multiplying both the numerator and the denominator, or the dividend and the divisor, both by the same number. How did you choose 10? How did you know you have to multiply by 10? That it's not. Why did you not multiply by 5? I mean, you do it so that 0.2 turns into a whole number, right? We do the same trick now. We turn the denominator, the number that we are dividing by, the bottom number, we turn it into a real number. And then when you think about how can I turn it into a real number? Okay, wait, okay. First, let me say division by, let us write division by, this thing keeps, I don't know why that happens. Division by a real number is easy. Say we have, I'll take the 3 plus 2i. Say I want to divide 3 plus 2i by, take any real number like 7. Like it's not even a even or a nice number, 7. What would the answer of this be? 3 over 7 plus 2 over 7i. Done. Right? But but division by a complex number is not, let's say, is not so obvious. Because if I have 3 plus 2, I divided by, what did I have earlier? 5 minus I.
Yeah.
How do I do this? Okay, so the trick is, here's the trick. I'm going to write, do the same trick. Do the same trick. That we do in decimal division. Division by a decimal. Do in division by a decimal. So I'm going to remind you how decimal, so if I want to do 23 over 0.2, I would go and multiply both by 10. And I'm actually I'm changing the question. Oops. Hi. Now it is 230 divided by 2, which is something I can do. I can't do this. I can't do 23 divided by 0.2 directly. So I change it into 230 divided by 2. Because now I can do it. That is 115. Right? So what we did here, we changed, not changed, we let's say we turned. We turned the decimal number into a real number. This into this, into a real number. Similarly, not a real, sorry, not a real number, whole number. My mind is the decimal number into a whole number. We turn the decimal into a whole because we know how to divide by a whole number. So similarly, you try to think, now I have to go to the next page. Yeah, it's also a real number, but 0.2 is also real now. There's no sense, all numbers are real on the real number line. 0.2 was also real. I didn't change it into a real to real, but I changed the decimal or the fraction, 0.2 is a fraction, into a whole number. Okay. I'm going to the new page. I hope you have copied. Okay. Similarly, when we have to divide by a complex number, if that denominator is complex, that's when the problem is. Complex number, we turn it into a real number. What do you mean what? We turn it into a real number because division by a real number, we know. I showed you here. Here, the first one, if what I'm dividing by is a real number, it's easy to do. The problem is when I have to divide by a complex number. So when I have to divide by a complex number, I will turn that complex number into a real number. The problem is, how do I do it? By what do I multiply? Just like I multiplied by 10 if in the decimal case, when I want to do 3 plus 2, I divided by 5 minus I. 3 plus 2I divided by 5 minus I. Tell me, how can I want to change this into, like, by multiplying by something. By what do I multiply to change the
Miss, you are in mute.
Thank you, Mihil. Happy is saying A, or what is that? Did you say A? Ayo, now I, it's a new Ayo.
No, he means like that happy thing. Hey, that way.
It's a happy thing.
Yeah.
Okay. Now what did I write? I had 5 plus, was it 5 plus 2i? I can't remember. Can you give me the two numbers?
Wait. Isn't that 3 plus 2i and 5 minus I?
Yeah, so tell me. 3 plus
2i over 5 minus I.
you have to think now. I'm trying to like get you to think about this. If I multiply both of these, by what can I change this
Conjugate.
into? Just a little, by the conjugate of that. Because I said the product of a conjugate pair always gives a real number. So just like in decimal division, you multiply the top and bottom by a 10 or 100 in order to make the decimal number into a whole number. Here, to avoid having to divide by a complex number, we first multiply the top and bottom by the conjugate of the denominator, because then it turns into a division by a real number, which we know how to handle. Is this clear? Why we do that? I don't think you learn why you do that. You just say, when you divide, multiply by the conjugate. And this is why we do that, because then we know how to divide it, because we don't know how to straight away do this division. Okay. So I can't remember, like, I think I wrote this and then you write in red, multiply. So this is the trick we do, part of the trick. Multiply both numbers by the conjugate of what? It's recording, right?
Yes.
Yes, miss.
Conjugate of the
denominator.
Denominator, the number that you're dividing by, okay, of the denominator. So when you have to do 3 plus 2i divided by 5 minus I, you first do 5 plus I. Let's put that in a different color, no? Five plus I, and also the numerator then 5 plus I. I'm not changing anything when I do that. On top I get, now I know how to multiply complex numbers. So on top I get no, no, no. Hmm. I will go this way. Am I doing this right? It's a coincidence that I am getting nice numbers here. It's half plus half I. Is this right?
Yes, that's the answer.
And this is the question you asked. How to turn this into a pure real number? That is by multiplying by its conjugate. So we are making the denominator a real number. I need to give you your break. So after you copy this, take a 5 minutes break. Okay, you've been working throughout. I had a little break earlier. So take a 5 minutes break and then we'll come back to this. Okay. Are you back? Oops. I think I took a break longer than 5 minutes. Okay, if everyone is here, I can't. Okay. If everyone is here, oops. Is everyone back? Can you let me know whether the 4 operations, how to perform the 4 operations with complex numbers, whether it is clear to you completely? I'm sure addition and subtraction is very easy. Okay, all of them. Very good, Malik. Others too, especially this division. I don't want you to just by heart, multiply, conjugate, just by heart. You have to know why you do that. Oh, this is why, you have to realize it. Why we multiply by the conjugate, not just know it as a way of doing it. Okay. Right. Then you actually have to practice this a little bit too, but I will give you that as homework. When I did this in school, I realized this was adapted from the early way we did. Very nice. I'm glad you already realized it. Oops. So you got it. Very good. Right. Then if you are not tired, we did a lot of theory, covered a lot of theory today. We were just doing a lot of theory. Shall we start the next little topic, which is how to find the square root of a complex number? It's very easy, a little short little theory part. I think we have about half an hour. We can finish that. And the rest is, yeah. Okay, then a new page, to a new page. Okay, finding the square root of a complex number. Finding the square root of a complex number. Oops, underline. That didn't go well. Let's do the underline. Finding the square root of a complex number. Now, before you think about this, can all of you go back and think about what we do when we have to find the square root of a real number? You use the calculator, that's what you do. Okay, when you want to think about the square root of a real number, like if you have a perfect square, like if I say, what is the square root of 16? If this number is a perfect square, if it is a perfect square, you know what the square root is. It's 4. And remember, by definition, the symbol square root returns the positive square root. We know that a number has 2 square roots, plus or minus the same number. But when you use this symbol, you give the positive square root. But 16 has 2 square roots, positive 4 and negative 4. But if I give you like square root of 17, you would use the calculator to find that, right? But you can find the square root of a complex number using a very special method, very methodical method. Okay? It nicely leads you to finding the 2. We know that any number has 2 square roots. Always there are 2 square roots plus or minus something. The same number positive of it and negative of it, right? You can very nicely find the square root of any given complex number. So that's what we are going to look at now. For this, you have to start with a little theorem. So let's write this little theorem. Now you will laugh at me when I write this theorem. It's like stating the obvious. Why is it a theorem? This is obvious. Why are we learning it as a theorem? You would wonder, but it is powerful. It's worthwhile to state it as a theorem. Okay. So I'm going to start with this theorem because we use this in this method. Theorem. A little theorem. Let's just write it. What this theorem says is that two complex, let's write with me, two complex numbers are equal if and only if they are real and imaginary. They are real and imaginary. Parts are equal. I'll just read that again. That is just it's obvious. I mean, if I say that A is unknown, I don't know what A is. If I say A plus BI is equal to 3 plus 2i, if I say that this complex number is the same as this complex number, that they are the same number, they are equal, they are the same, what must A be? What must B be? Obvious, right? So if they are the same, so A must be 3 and B must be 2. I mean, how else can it be the same number? It's like if I say, no, that's it, right? So is that clear? It's actually stating the obvious, but you will see how this comes in handy in this method that we are going to learn how to find the square root of a complex number. Okay, so let's have this on top, and then we are going to now find the square root of a complex number. We will just do an example. So through the example, you will learn it. Okay, so let's take a complex number and let's see how we can find its square roots. Example. Here this little thing gets written all the time. I don't know how to avoid it. Example. Find the two square roots. We know that any number has two square roots. Cube roots, 3 cube roots, and so on, right? Square roots, there are 2. Find the 2 square roots, SQ of, here's my number, 8 plus 6i. 8 plus 6i. It's a complex number. Find the 2 square roots of complex numbers. So I want you to find basically this. What is the square root of 8 plus 6i? Okay, what are the 2 square roots? And here's how we do this. Okay. We start with supposing that one of the square roots, now the square root of this number must also be a complex number now, so it must be a number in the form a plus bi now. Okay, so I'm going to suppose suppose that 1 square root of 8 plus 6i is, let it be a plus bi. Okay, is a plus bi, a plus bi. We suppose that one of the square roots is a plus bi. Are you with me so far? Any number has 2 square roots. We are going to find the 2 square roots of this number over here. I assume that one square root is a plus bi. Then the other square root will be negative of that. Square roots always appear as plus or minus of the same number. So we know that much. Okay. So if one square root is a plus bi, the other square root will be minus a minus bi, minus of this number, right? Okay, so if this is a square root of 8 plus 6i, that means this means if I multiply a plus bi times a plus bi, that is correct, Niti. Very good. That means now if a plus bi is a square root of 8 plus 6i, then if I multiply a plus bi by itself, I should get 8 plus 6i, isn't it? Okay, this means a plus bi, if I square it, it should be equal to a. I should get that. Clear? Now, if you, because we are working with complex numbers, if you feel like it's getting confused to you, always go back to a real number example and think about it. We are talking about the same thing. What I'm saying is this. Say you want to find the square root of 9. Now, we know it is 3 and minus 3. Suppose we don't know. Then if we assume that it is some number x is the square root of 9, then I can write that x squared is 9, isn't it? That's what I did here. Okay. Now I just work with this. Okay, let me expand this. This means a plus bi times a plus bi equals 8 plus 6i. I mean, I didn't have to write it like that. I could have just, actually, let me, yeah, it's not good to write like this. Yeah, this is advanced level. We know how to do that. This is a squared minus 2 times, sorry, plus 2 times abi plus b squared I squared, isn't it? That is a squared plus 2 times abi minus b squared is equal to 8 plus 6i. Okay. Now on the left hand side here, let me write it in the form real part plus imaginary part I. Okay, because that is that must be also a complex number. So do you see that a square? Now this is the only part that has I in it. So that 2ab is the imaginary part of that number. If I bring this here and write a squared minus b squared, that must be my real part. Plus I'm just putting brackets so that you see it clearly. Okay. Shall I use 2 colors like I used to do? Let me actually, for the real part, let me use, so the real part is a squared minus b squared, and the imaginary part is 2ab. Are you with me so far? This is the real part of the number on the left hand side. On the left hand side, I have a complex number. So I nicely separated and wrote the real part and the imaginary part I. Now, from this theorem, if the number on the left-hand side is the same as the number on the right-hand side, the real part of this number must be the same as the real part of that number. And the imaginary part of this number must be the same as the imaginary number part of the number on the right-hand side. Okay. So we are applying that theorem here. So let's write for. Can I go to a new page? It's difficult to write here. Can I go to a new page? Have you all finished writing what is on this page? Okay. For the complex number on the left side, to be equal to the complex number on the right side, from that theorem, we know that their real and imaginary parts must be the same. Their real and imaginary parts must be the same. So let's equate. What did we have? So the real part on the left-hand side was a squared minus b squared. It must be equal to 8. And the imaginary part on the left-hand side was 2ab. That must be equal to 6. This gives us 2 equations of a and b. If we can find a and b, we would have found the square root, because we supposed that the square root is a plus bi, right? So to find the square root, I have to find what a and b are. And now I have 2 equations of a and b, a pair of simultaneous equations of a and b. By solving this, I can find what a and b are. Can you solve this? Yeah. Do substitution method. That would be, let me do this in a different color altogether. Substitute, from 2, let me make a the subject, 6 divided by 2b, that is 3 over b, and let me substitute sub this in 1. Then I get a squared is 3 over b whole thing squared minus b squared over 8. Can everyone solve this, please? This is 9 over b squared minus b squared equals 8. Multiply by b squared, everything. I get 9 minus b to the power of 4 equals, okay, Nithni has already found. Yes, you are right, Nithni. You are right. 8b to the power of 2. What is this? This is a quartic equation, isn't it? B to the power of 4 plus 8b to the power of 2 minus 9 equals 0. This can be viewed as a quadratic in disguise. Okay, if I go here, if I do a small relabeling, if I call b squared with something like t, what I have here is a quadratic. I can write it as a quadratic. This is t squared plus 8t minus 9 equals 0. You can use the calculator to solve these quadratics. But this factorizes nicely. T plus 9. What is this? T plus 9, t minus 1 equals 0. I get t is equal to minus 9 or t is equal to 1. Then if I bring back my b squared, t is nothing but b squared. B squared is minus 9 or b squared is 1. What is my mission here? I want to find the values of a and b. If I have the values of a and b, I have the square root of 8 plus 6i. Now, I have two branches here. What can you say about this branch? B is square root of negative 9. But this is not a real number. It's not a real number. It's a number, right? Now we accept this as a number. Now this is an imaginary number. But we don't accept this as an answer for B. Tell me why. Can you go back to where we wrote suppose
Yes,
the
you're
square?
lagging.
Oh, I'm lagging. Oh. Let me wait for a moment then. How about now?
Much better.
Better? Oh. Something must have happened, no, to the connection then? Sorry, I didn't realize it. So what I was saying here was this, huh? Now we have two branches now. B squared equals minus 9 or B squared equals 1. Now, if you go along this branch, we get B is equal to square root of minus 9. And there is plus or minus in the front here. But we know that this is an imaginary number. And I'm saying we don't accept this. Tell me why. We don't accept this as an answer for B. But on this side, B is square root of 1 plus or minus. Yes, very good, Hatvi and Methni. You have been like monitoring all this very closely. This is plus or minus 1. That is okay. We accept this, but we don't accept this. Let me go another. Let me actually write this one more step further. This means plus or minus. This is actually 3i. And we do not accept this. We do not accept. Do not accept. This we accept. This we accept. So this side we don't accept. Why? If we go back, I have supposed here that a plus bi is my square root. Remember these two numbers, this a and b, they have to be real numbers. A and b are the real part and the imaginary part. The b is the coefficient of I. B by itself is pure real. It's like it's a real number, 2 or 3 or minus 10 or half or 2/3 or 0.75 or, right? If let us remind this here, A and B belong to the real numbers, okay? But here B, we got an imaginary number. So that's why we don't accept it. A and B have to be real numbers. So these two I can accept. I'm going to the next page. Is that okay? Okay. So I will continue with the two. So I got B is equal to 1 or -1. That's the only answer. Two answers are there. These are the only two answers I accept. That's fine. That's fine. So I'm glad to hear that you didn't follow my steps. You just went and solved it the way you wanted. Now you would have solved it in a different way, and you may have gotten answers for A first. Then let's find the corresponding values of A. So when B is 1, what is A? A is 3 over B, 3 over B. A is 3 over B. That is 3. When B is -1, A is 3 over -1. That is -3. We now have the two square roots. Therefore, let's write. Therefore, the two square roots of 8 plus 6i are 3 plus I and -3 minus I. I'm using A and B to write A plus BI, A plus BI. They are the positive and negative of the same number. You can, if you like, you can write plus or minus 3 plus I. We are used to writing like that now. Plus or minus 2, plus or minus 1, like that.